dear attendees. I work in the internal audit department. Today I'd like to tell you about the role of AI when searching for fraudulent activities by looking through outliers. Let's consider the ways to solve this problem. Quite often, an auditor's work implies looking for some outliers in data. We have huge data selections. It could be statuses of applications, history of transactions. You need to understand that all the activities described there are exactly as we expect. Let's consider the main problems that we encounter. That's outlier analysis, search understanding, and finding the reasons of the appearance. Look for outliers as an end goal. Outliers can be brought about by errors in data, by wrong rounding, or by noise, by errors in classification, or by software faults. Also, the search of outliers can be done as an end goal. For instance, when we are this type of problem is sometimes part of the business process. Outlier minimization for the further training of the model, reducing the risk of its retraining. This kind of problems is quite typical. This way we can achieve greater accuracy through filtering out the data that can bring in problems in our investigation. But the most important task is to look for banking fraud, looking for non-standard players in the exchanges, and so on. Also, you can use the ways to solve this problem in any other area where you need to identify outliers. In the general case, the outlier identification problem can be defined as a problem whether to identify the behavior that is different from the usual one. One can talk about two types of such problems. That's outlier detection, when the outliers are observed as other type of behavior or features than most have, or to identify novelty. In this case, the data to train the model are not contaminated with outliers, and we're interested in identifying if the new observation is an outlier. In this context, the outlier is the same as novelty. In many papers, outlier detection is regarded as unsupervised learning, but in practice it's not always this way. In their work, auditors can encounter situation where part of the data are marked up, and based on them you have to identify the model. This model is usually done through building a binary classifier that will split the selection into classes. But if there are no marked up data, then this task can be classified as unsupervised learning. What are the methods that you can use to solve the problem of outlier search? You see that visualization and statistical methods are identified separately here, but there are also modeling methods, distance-based, density-based, and model-based. I'll speak in more detail about each of them further on. Let's consider in more detail the visualization for outlier analysis. For this presentation, I used an open data set for fraudulent transactions. So, in the first picture, you have a box with mustache. Based on this diagram, we can make the following conclusion. Average values, median, of the 25th percentile, and so on. Are there outliers at all, and where they are? We can assess the symmetry of the data set. We can speak about the density of the grouping, or determine the offset. The next type of diagram in this slide is a distribution histogram. It allows you visually assessing the data. We can say certain things about the distribution of our observations, modes, scattering, symmetry. We can identify obvious outliers. Also, using this distribution curve, it's easy to determine the average, the median. But these ways are only good for primary analysis. Quite often they're not enough, because they allow representing only unidimensional dependencies on the data. And we have to work with each variable separately. But unfortunately, it's not always good. There's a probability that only a set of variables will give you information about outliers. Quite often, data sets consist of a very large number of features. That's infinite n-dimensional space. This stands in the way to build adequate models. There are algorithms that allow you reducing the dimensionality without losing a lot of data. So basically that allows to simplify the work of a model and the speed of calculations. This will also allow us to visualize the data. This slide shows the result of two algorithms, TSNE and PCA. I reduced dimensionality to two features, and this allowed us to see how well the data are separated in these scatter plots. Here we see that one of the algorithms has split the data quite well. Let me speak in a bit more detail about that. This component analysis, we call it the main component method here. So using this, we can find a smaller dimensionality subspace where the quadratic deviation can be minimal. Why do we need this algorithm? It allows you to reduce the number of variables by having chosen the most variable of them. The second algorithm shown in this slide is the TSNE algorithm, that stochastic nesting algorithm. The stochastic nesting algorithm is an effective method to visualize large sets of data. It successfully finds Latin structures in data, shows groups, and identify non-linear changes. As we can see, the TSNE can easily cope with fraudulent cases on your data, separating them from non-fraudulent. Even though the selection was quite low, the TSNE algorithm did quite a good job identifying the clusters in our scenarios. This gives us an idea that future prognostic models are going to work quite well when separating fraud from non-fraud. Next slide. It's about a different algorithm that can also be used when looking for fraud. It's k-means. It is part of the distance-based methods. They're based on the distance to the cluster center. We find centroids or clusters of standard observations and calculate distance to them. If the distance is more than a threshold, then we believe it's an outlier. The k-means algorithm splits the algorithm to the preset clusters so as to minimize the deviations at the end of each cluster. So for each iteration, you recalculate the mass center, then vectors are split into clusters again, depending on which of the new centers became closer. So the drawbacks of this method include a strong dependency of the initial cluster centers, The optimum selection is not known to us, and of course the number of clusters must also be known previously. But because in our case we know for sure that we only split transaction into fraud versus non-fraud, we're only going to have 2 clusters. So basically this drawback doesn't apply in our case. The slide shows that the algorithm has identified anomalies quite poorly, or better to say, hasn't identified them at all. There's not a single fraud case here. It just confused them. It swapped their places. Those values that should be shown as anomalies, as outliers, are shown as regular observations, and the other way around. Density-based methods. They are similar to distance-based, but the computation is done not based on the distance from the cluster center, but on the density. If the density is lower than the pre-set threshold, it's considered to be an outlier. So this algorithm based on density is called DB-scan. And we see that DB-scan doesn't do a good job working with our data, but let's consider the following methods. Let's dwell on the one class SVM very briefly. So, to be brief, SVM is a base linear model based on the algorithm in terms of classification, which has to split the classes in such a way as to maximize the distance between them. Initially, the algorithm was only capable of separating classes in a linear way. The method has become more popular after kernel tree was introduced that allowed to deal with nonlinear classes. Kernel tree is a function that can transform the space without feature transform. It's quite effective in terms of computing and allow identifying spaces of different dimensionality, the feature spaces. One class SVM. It's one of the forms of the classic algorithms. But what follows from its name, it's enough to have just one class to train it. If we're dealing with a problem where we only see good data, have good data for training without outliers, we can use this model and learn for every new observations to identify if it's an outlier or not. The general idea is to transform the feature space, as I said, and to draw the separating hyperplane in such a way that the observations should lie farther from the point of reference. What is closer to the point of reference and lies between the center of reference and the plane will be considered as outliers. We're now going to see a video that's going to show how the isolation forest looks. The isolation forest algorithm isolates observations and then randomly selecting the difference between minimum and maximum object.
So we isolate it in a simpler fashion because to select them, you just need to go through a few iterations. On the other hand, to single out a normal one, it may require a big number of iterations, so it can be measured as a number of instances required to divide them and set them apart. This algorithm creates the isolation trees or random decision trees. Then we measure it as the length of the path to isolate. We may compare one class SVM versus SVM. Right here, I'm showing here the proximity matrices. So these matrices, as far as we can see here, divide, set them apart, and they generate a far superior result, which we have achieved by setting the parameters With the random forest one, it's contamination, which is the main parameter. One class SVM has a different one. It affects the models, and previously I just took the sampling approach, 50-50 approach, and I was selecting those parameters, judging on those parameters. I would like to voice the one class SVM. Thanks to one feature, this model provides much better borders, and it's convenient to use when you don't have too many outliers there. When we have pure selection, to use the standard approach. What would be the disadvantages? It could be creating quite a lot of false negatives. What we need to stipulate initially that this data set does not create too many outliers. As far as isolation forest is concerned, we have the non-linear borders, intuitively clear principles, and convenience of use when binary classifiers are not applicable. We would like to point out, unlike one class SVM, isolation forest does not require pure data set. The main minus here is a very difficult setting of the parameter. It's not possible to do it without actually having any information about data and about outliers by setting the contamination parameter. In the end of my presentation, I would like to say that the defined method to guarantee the success does not exist, but hopefully one of the methods I have voiced will help you find some fraud in your data. And thank you very much for listening.